Hello. Yeah, good evening, everyone. So, we'll be starting in a minute only. So, let me give some time to share my screen. So, today is our week 6. Okay, let's start today's class. So, so today is our week 6 of this NLP course. So, like other weeks only, we'll be starting from solving some questions. Yeah. Uh, so, so this is the first question. So you can try this one and write the answer in the chat box. So then I'll solve it. So this is the first one. So in this week you have learned about the dependency grammar and parsing. Then you have seen the transition based parsing formulation and transition based MST based dependency parsing. Okay. So the question is about which of the following is or false about the criteria of head and dependency in a construction or in a dependency graph. So I think you know about what is phrase structure representation. What is a phrase structure? Then from the phrase structure, uh, we create the dependency structure representation. There are some criteria for heads and dependents. So we'll see that. So, so to answer this question, you have to know what are the head and the what are the dependents. Okay, so we have to think. That is Okay, so Lalita is saying that answer, this one is correct. Okay, okay, fine. So this one is false. So H is obligatory and D is mandatory. We'll see. We'll see in a say soon. So so first we have to see that what is a we have to see first. I think it is important to know what is the your one second. So first come that a phrase structure. Phrase structure representation. So what is a phrase structure representation? So I think you have already done in the class already. So like if a sentence is like economic news had little effect on finance market, then from here the dependency become that. So dependency, so from here like something like this. So this is the phrase structure. Okay, okay, fine. Now how dependency structure, what is this is the phrase structure. Now comes the dependency structure. What is a dependency structure? Like add, news, economics, effect, little on market, financial. Looks like this. Fine. So this means that this has dependencies of subject, a mod, object, then a mod like this. Okay. So this is basically the yeah. So this is basically uh, the dependency structure representation. Now we have to see what the dependency structure look like. That is, if a sentence like he sent her a letter, then dependency will look like this one. Like who sent to her, then sent to he. So this is subject, then this is object, then this is the object, letter, then we have a punctuation. This is the full stop, then this is punctuation, then later element. Okay. So this connect the word in a sentence by putting arrows between the word. Okay, so dependency structure connect the words in a sentence by putting arrows. So we have put some arrows. So then how the arrow? So what is this arrow? So this arrow shows relations between the word and are typed by some grammatical relation. So these are the grammatical relations. Okay. Now arrows connected a head like governor, superior, or regent with a dependent. Dependent is modifier or inferior or subordinate. So, so these dependencies usually form a tree. So there are some criteria for heads and dependents. So what are those criteria? The head determines. So yeah, so we have two things. One is head and another is dependence. Okay, we have two things, head and dependent. So head, so this head determines the synthetic category of C, and H can replace a C. So C, okay, another is construction. Okay, so construction or C. So the criteria for syntactic relation between a head H and a dependency D in a construction C. So this whole is a construction. Okay. So head determines the syntactic category of the construction. Okay. Head can replace the construction. The dependent specifies the head. Head is obligatory. Dependent may be optional. Okay. Head select the dependence and determines whether the dependent is obligatory or not. The form of dependence depend on the head. The linear position of dependent is specified with reference to head only. Fine. Now our question was that from these which are the false statement. So this head in a dependency construction, every construction must have a head. Okay, that's why the head is considered obligatory. So head is considered obligatory. Why? Obligatory means you always need a head to form the construction. Now we have dependent. Dependent means D. So while the head is required, but its dependent are not necessarily always present. Dependents are optional in many cases. Their presence, the presence of the dependents depends on what the head select. This means the dependent is not mandatory in every construction. So first statement says that H is obligatory and D is mandatory. So this is false because we have seen that D dependent is optional. Okay, and obligatory means that you always need the head to form a construction. Fine. So here the only head is required. Dependence may or may not appear. So in some cases, the second option says that a, the head selects the dependent and determines whether dependent is obligatory. So it's true because the head select its dependent. So head only select its dependent. This statement is true and determine whether dependent is obligatory or not. Okay. So it's his responsibility to find out the dependent is obligatory or not. So based on the construction's requirement, it can determine if a particular dependent is obligatory or optional. Fine. The form of dependent depends on the head. The form of dependence depends on head. It's true because the feature or form of the dependent often rely on the head only. For example, the head might assign a particular case or agreement to its dependent. Right now, H specifies D means head specifies the dependent. It is a false statement. So it's true, but it 4 is also a false statement. Okay, means the correct relationship in the dependent specifies head. Like so, what I mean that while the head select dependents, it is dependent that provide additional information or specification for the head. Okay, so D basically if it was D specifies head, then it should be true. Got it? So the final answer is 1 and 4. So what we have understood from this that head is the essential, but not every dependent is compulsory. And the head determines selection, while the dependents help specify the properties of the head. So 1 and 4 is the option. So 1 and 4 are the false statements. Fine. So now move back to our second question. Second question says that is question number 2. Which of the following are true about formal condition on dependency graph G? G can be cyclic, G can be projective, G is disconnected, G obeys the rule. If I then J, not K then J, for any K not equal to I. So which are the from these which are the true statement? We have to specify it. So here we are talking about the dependency graph. So you can write your answer in the chat box. So Lolita is saying 1 and 2. Lolita, you are incorrect. Okay. So yeah, we'll see. Okay. Let us check. 2, 3, and 4. So we have got some options. We have got all options basically 1, 2, 3, 4. Okay, let's see. So first find out that yeah. So what is the dependency graph? So we are talking about the dependency graph. So a dependency structure can be defined as a directed graph G. Okay. So dependency graph is a directed graph. Okay. Directed graph means that you have the edge should have the direction. Right. Now a set of V of so we have so the graph is represented by node and edges. We all know. Now, what are the label graphs? Node are labeled with word forms. Okay, so this is a node. So this is a label of word forms, and the edges are labeled with the dependency type. Right. So this is the dependency graph. So node has the word form and edge has the dependency type. So everything will be every node will also have a label, edge will also have a label. Fine. Now a dependency structure can be so we know the notation. So we have used some notation here kj. So we know that notation. I think so. If you say arc means the edge of a graph widwj. So this links uh so head wi to dependent wj. So wi is the head, wj is the dependent. Got it? And with label d. So d is the label. So how should I represent it? This. So I can represent this one like wi, where wi is the head and wj is the dependent, right? D is the label. Got it? That means I to j, ij belongs to A. Fine. Now, there we have some formal condition on dependency graph. What are the condition? Conditions are condition for dependency graph. So G is connected. That means for every node I, there is a node J such that I. So for every node I, there there exists a node J such that if I tends to J or J tends to I. Fine. G is connected, then G is acyclic. That means it doesn't form a cycle. Fine. That means if I tends to J, then we should not have a case that J also tends to I. Okay, this should not be a case. That means it will, otherwise what it will do, it will form a cycle like this. I to J, J to I. So this is I, this is J. We should not have case like this. Fine. And G obeys the single head constant. G obeys single head constants. That means if I to j there is a edge, then not k to j. That means this is I, this is j, this is k. If I to j there is a edge, then there should not be a case like this. This should not happen. This edge should not be there. There should be always a single head. Okay. And G is projective. Okay. That means if so again I will give this same example. I, j, k. So if I to j there is a edge, then j to k, then it should be a case for any case such that both j and k lie on the same side of I. Okay, that means this should not be the case. That means what I want to say. So I is basically j is basically on the left side and k is on the right side. I am showing that so this is left side, this is right side. So that's why this should not be the case. What it should be? It should be like this. I j k. It should be always in the same side. Got it? That means the projectiveness. Fine. Now tell me the answer. I have tried to describe all of this. Like anyone who has not answered, they can answer from this one. Okay, so the correct answer is 2 and 4. Got it? Because G is connected and acyclic. Hmm? G is connected and acyclic. That means I have shown that what does projective means. So projective means what is projective. So I think you know that why I'm saying 2 and 4. So 2 and 4 is the correct answer. Yeah, fine. Next, come to the second question. Mm, Okay. So do you know that what is that this algorithm is truly advanced algorithm? Why there is a need of truly advanced algorithm? Mm, okay, okay. Let's finish this question. Then we'll be going to the in depth of this algorithm. Fine. So so the first statement is saying that deterministic parsing requires an oracle, and then oracle can be approximated by a classifier. Oh, fine. So in deterministic parsing, especially in transition-based dependency parsing, an oracle is used to provide the correct parsing decision at each step. So why oracle is used? So this gives the correct parsing decision. Fine. It the oracle gives you the correct parsing decisions at each steps. Okay. This oracle is approximated by a machine learning classifier during training. So I think in the lecture videos, the professor skipped this part, like not skipped. So he said that when I was also watching the videos, I have noticed that he's saying that the how the oracle is generated. So we will see it later. So so this oracle is generated by a machine learning classifier. Okay, so this happens during training. Okay, so that's why this statement is true. Deterministic parsing requires an oracle, and this oracle can be approximated by a classifier. So this classifier is basically the ML based classifier, right? So that's why this statement is true. The second statement is each vertex is each vertex in the graph greedily selects the incoming edge with the highest weight in the Tuliu inverse algorithm. So in this algorithm, for finding a maximum spanning tree of a directed graph, every vertex except for the designated root initially select the incoming edge with the highest weight. So that's why this statement is also true. So so this mm, yeah. So if you don't know about this algorithm, I'll just describe after or I can describe it here only. Yeah. So it will take some time to describe this algorithm. So this algorithm is really very big one. So okay, so what is this algorithm? So we are discussing uh, Shu Liu Edmond. Right. So the problem definition is like this. First, we have to define the problem. What is the problem here? So we have given a connected directed graph. So the graph G, so you have some vertices again. So this is connected and this is directed. Okay, you know what does it mean by connected and directed because I have already discussed it just now only. So I'm not going into that part. Then we have some vertices. So these vertices is basically belongs from V1 to Vn, and this edge belongs from E1 to Eij. Correct. So for these vertices, this edge to the two vertices is connected by a edge only, and every edge have a weight. Got it? So I have already shown you here. So every edge will have a weight. So this D. So here for this D we denote is by Wij for each cases. The goal is to find the maximum spanning tree. So here using the graph, our goal is to find the maximum spanning tree. Okay, so we can denote it by T, Et, where all the vertices are connected and each node. So what should be the condition here? V are connected and each node except the root node has only one incoming edge. Then the sum of weights of the edges is maximum. So what is my point? Each node except the root node has only one incoming edge. Got it? Now the sum of weights of the edges is maximum. So this should be my condition. Right? Okay. So yeah. So now from this, okay. So uh, so let me first draw a graph. Okay. So example graph. So I have the head, or this is a root. I must have a root first. Then I have node number two, node number three, and node number four. Okay. Now for this, my weight is 10. Now from here, my weight is 8. Fine. Now for here, this, my weight is 2. For this, my weight is 4. Fine. Now for this, my weight is 7. For this, my weight is 6. For this, my weight is 2. For this, my weight is 3. Now, for this, my weight is 10. For this, my weight is 12. Now, for this, my weight is 11. And for this, my weight is 9. The graph is clear to you? Fine. So we will this algorithms is designed in a this Chulu algorithm is designed in a recursive manner. Okay. So this is the example of a fully connected directed graph where we have four vertices, 1, 2, 3, and 4. Fine. So what should be the first step? So let what I have to do. Fine, you got it. Okay, this was our first graph. So which was directed and fully connected. Okay. Now, first step is given this graph. What is the step 0? Given the graph, the first step is to decide the start point. Is that the root of the tree? Fine. It can be predefined by the user. Otherwise, the root is the node with the highest sum of outgoing edges. Okay. So here I have given the root node. So if I don't give you this information that this is sorry, that this is a node, this is my root node, then how will you understand? So the rule for this is that how should I understand which one is my root node? I should understand that I should found out the node with highest sum of outgoing edges. This means R is equal to argmax vi belongs to p for all vertices. I have to sum its the edge weights. This pj belongs to p, right? Then as the root can only have the outgoing edges, we remove all the incoming edges of the root. So if we remove all the incoming edges, that means I have to, so this is the incoming edge. So I have to remove it. This is the incoming edge. So I have to remove it. Clear? clear to everyone? Now what I have to do? So this is my step 0. So here the same thing I have to do. Right? Now what is my next step? So this is the resulting edge after doing this. Okay. So then what is the next step? So the step 1. So what is the step 1? Body I guess. Body So what is the step 1? Step 1 is first we first we start from the graph mg with the maximum incoming edge. Okay. So we start from the graph with the maximum incoming edge for each node other than the root. Is that for each node vi there is only one incoming edge from node vi. So and it is the edge with the maximum weight. If the graph is a tree, then it's a maximum spanning tree. Otherwise, the graph contains at least one circle. Then we need to break the circle by replacing certain edges with edges outside the graph. Fine. What I mean basically, yeah, if I show you like this. Oh, sorry, I also forgot to remove this one. This one was also an incoming edge 11. Fine. Now see, my root node has no incoming edge. All are outgoing edges. Fine. So in this, so you look you notice these green edges in this graph. We can define the circle between node 2 and 3. So with this node 2 and node 3, we can find the circle. Are you getting the circle using this one here? Here. Any problem? So what I have to do in step 1, so I have to see what are the maximum incoming edge for each node. So I can see there for node 3, incoming edge 1, 2, 3. For this one, 1, 2, 3. For this one, 1, 2. Okay, fine. So I don't take care of this node 4. I will be concerned about node 2 and node 3 because first I have to see that which node has maximum incoming edge. Any problem? So I can see that this graph is not a tree. There is a otherwise it is so what I'm saying that for each node vi there is only one incoming edge from node b denoting so the node will be denoted by e and it is the edge with the maximum weight. So this should have a single incoming edge which should have the maximum weight. If this is not the case, if this is not the case, then what we do? Then we need to break the circle by replacing certain edges with edges outside with edges outside the graph, outside this graph. So what we do, so this one is little basically. So what I do, we first randomly pick one circle. Okay, we randomly pick. So we have two circle here. So we randomly pick one circle. The circle is means that circle should contain the node, the vertices. P1, C2, P3, C3. So these are the vertices. Here I have node 2 and node 3 like this. Okay. The circle itself is optional, and we only need to break the circle with the minimum cost. We have to break the circle with the minimum cost. So what is my objective here? My objective is to break the circle with minimum cost. Fine. Now to achieve this, we first build a new graph G dash. We will build a new graph G dash. So here in this G dash, we will treat the circle as a new node VC. In G dash, how will I treat the circle as new node? Yes, treat the circle as a new node, and I'm like this the VC. And then find the maximum spanning tree in the new graph G dash. Find the MS tree in new graph G dash. Got it? So that's so then recursively then again follow this step to find this out. Now we first describe the way to build a new graph where we have to, from the vertices set, we have to discard the circles and all. Okay. So so how can I find the circles and all? So basically, it happens that, so how to build new graph G dashed, where V dash is the set of vertices and E dash is the set of edges. With vertices, so this V dash is, we have the old vertices. So these are the old vertices 1, 2, 3, and 4. From there, I I subtract the circle corresponding vertices. So for each edge, now what I have to do? We can split them into 3 cases. So the cases are for edge SD in E, if A does not belongs to the circle node and D belongs to the circle node, then add an edge E dash is VC to E dash with weight. So what should be the, so for each edge ESD, so I have to find out the edge. For that edge, if one side of this edge that is S, that is belongs to a circle node, that does not belongs to a circle node, and the other side of that edge D belongs to a circle node, then we add an edge E dash STC to E dash. Okay. So then we have to give the every edge here, every edge here has some weight. So the weight is E dashed is BC. Okay. So this is a negative value. Now, so let's see what's happening here. Then we'll write the theory then. Okay, first what we have to do that I have to finish the incoming edges. These were the incoming edges. Then I had the cases of making circle. So these were making a circle. Then what are the situation? So here one circle formed by, so the circle was forming by node 2 and node 3. So we treat the circle as a new node BC. Fine. So this circle, we treat this as a new node. So this will be a new node. Fine. So then how then what will be the representation of that? The representation will be like this. So if I get it as a new node, then it will become, so one is root, this is BC, this is our new node. So this became BC. Got it? So this circle become a new node. Got it? Any problem? Now what are the other things? So this was like, so I have to put a I have to give a weight here. I have to give a weight here. I'll show you how will I give a weight here. I have to give a weight here also. Then I have to go for weight here also. For this also. Then for this also. And here I had 9. So this 9 is coming from here only. Right? Got it? So you know that from where 9 is coming, 9 is, so this 9 is coming here. No problem? Okay. So now I have to fill in the blanks. I have to give the edge some weight. So how can I give the give the edge some weight? So that's why I was describing you this one, that how I can give the edges. So this is WESD minus WE5ESD. So this is nothing but for edge ESD in E, if S doesn't belong to C node and D belongs to C node, then we add an edge E dash especially to E dash. So this edge is nothing but E dash is BC. So we add an edge here. E dash with weight something. So what is this something? So this is nothing but W of ESD. So what was the W of ESD? W of ESD minus W of E pi VD. So what is this? So what was the weight first? It was 10. So can anyone tell what should be the weight? Okay. So yeah, let me tell you. So the first case is this. So if the source is not in the circle, so here it says that source not in the circle and the destination is in the circle. So this is the destination. The destination belongs to the circle. Is that in edges for C, there is the incoming edges for C, then we only keep one edge from each node that is not in C to the new node VC with the largest difference GUV minus the list of all the incoming nodes. Okay. To specify for each node U in VC, there is an edge between U and VC if and only if there is an edge between U and any node B in C. So how that this is calculated? Uh, right now what happens then we have another two cases. So the second case is, what is the second case? The second case is if the source is in circle, but the destination not in circle. Is that outage for C? Then we keep only one edge from the new node PC. Okay, so each node that is not in C. Okay, that means key the weight of the edge BC to B is equal to maximum in U in C or in fine. Then we record the edge VCV originally with the edge UV and then take the argmax from there. And we have also a third case where we if the source and destination are all not in the circle. So source and destination not in circle. Then just add edge to now. So these are the cases. Then we will do this recursively. Uh, and yeah. So from here, what will happen? So from these, we can get. Then we need to find the maximum spanning tree for this graph. We have to find the maximum spanning tree. So what is the maximum spanning tree for this graph? So maximum spanning tree will be for this graph will be maximum spanning tree is minus 2. Then I have the 9 here, minus 3 here. Got it? So this is the case. And then what we do that that last step is without so we assume that incoming edge of BC in this graph is from node VS and its corresponding edges in the original graph G is ESK, which with this node belongs to the circular node, which creates the circle. Then the edges of the final tree is formed by combination of the edges in A and replacing the edges from VC, and the edges in the circle without the incoming edge of PK. So from here, what we get? From here we get like this one. We have the so first delete all the incoming edges. Fine. Then this will be here and other things. So this one. So this will be your uh, maximum spanning tree. Okay. So now let us try to so, yeah. So to solve this, we had this one. So each vertex in the graph greedily select the incoming edges with the highest weight in the Chew-Liu-Edmonds algorithm. So in the Chew-Liu-Edmonds algorithm, for finding the maximum spanning tree for a detected graph, every vertex except the designated root initially select in the incoming edge with the highest weight. So this is also a true statement. Okay. Now during the iteration of this algorithm, it never produces cycle. So this statement is false because the algorithm produce cycle in the initial greedy selection phase because it select the edges greedily. When a cycle is detected, the algorithm contracts the cycle into a single vertex and continues to process. And cycle are indeed produced during the iteration before they are contracted. Okay, so this is a false statement. Fine. Now, a multi-digraph is where multiple arcs between vertices are possible. Uh, then, so this is by definition, a multi-digraph is a digraph where multiple arcs between vertices are possible. Okay, so this statement is also true. Okay, so the correct answer I think the three. Okay, now let's try to solve this one. Try to solve this one. Okay, so Bala has you had some question. Okay, so yeah, I didn't respond because I have given the question to solve you. So I didn't look into the chat. So if I have a question that how two-step weight is calculated from 1 to BC, how it is minus 60. So so you had so I you also didn't answer this question. Is it visible to you? So let me share. Give me a second. So I have given this question to you. Okay. So you should be trying to solve this. I gave you 10 minutes because to solve this. Okay, so I didn't look into your question. I didn't look into the chat. So your question was that how this minus 6, 3, minus 2, 2, this came. Okay, fine. So this needs some time. So if you didn't understand this algorithm, let me describe you again. So the thing is that how we will be just focusing on the how the reweighting or adjustment work, that how reweighting. So this is clear, right? Like this is clear. Like if we found a cycle, we make the that we treat that as a new node. So until this is clear, then we our new node was VC. Fine. So the question is how I so I found a new node. Then how should I what should be the weight of this new node? How should I find the weight of this new node? Is it your question? Okay, fine. So the thing is, so how we so this is called the reweighting of the edges or edge adjustment. Okay, so when a cycle, we have got a cycle. So I name this as cycle C. Now, when a cycle C is detected and contracted into a single node, this single node is VC. We need to define a new weight for the edges. So, so for which I have to define a new define the new weights. I have to define it for from a node X outside C to VC and from from VC to node Y outside C. C means circles. So this is the C. This is your C. So this says that from a node X outside to C, this one, and from VC to node Y outside C. Okay, that means these ones. Now, suppose we have a edge X to V. So there are three cases arise. Okay, like we some in this circle, some edges is outside the circle, and so for this kind of thing, maybe this belongs to the circle, but this does not belong to the circle. So this happens basically. So this does not belongs to the circle. This root one. So for that case, what I do that that's so for maximum uh, so for the maximum absorbance, it is off. So basically, what I have to do before concatenation, the cost or weight of using X to B in the final tree must also consider in the cycle C. We for each node in the cycle, that means 2 and 3, 3 and 2 and 3, uh, for each node into the cycle, U belongs to C already has an incoming edge U to U. So these are the incoming edge 12 and 10. Okay, this is Tuesday. Then For the maximum absorbance, it's often explained by the minimum version, like except we take the maximum instead of the minimum. So what I mean that is like the new weight W dash X BC. So X is what is X? X is outside C is equal to W of XV, what was previous, minus W of PP V minus delta. So this PP, so this PV is the parent of V within the cycle. Fine. And the age chosen in the cycle for the subgroup. And this delta, what is this delta? So delta is the constant that ensures we do not double count the contribution of the ages we have already chosen. Okay. Now how to so this is the formula basically to choose it. Okay. Now what to do here? So in our cycle 2 and 3, so this weight is 10. This weight was 10, this weight was 12. Then minimum of 10 and 12 is, so what I have to do? I have to find out the minimum of 10 and 12, which is 10. If we, so there are, so basically there are two formulas. So, so basically I am talking about this one. So there are two formulas, like W mean is equal to minimum of U belongs to C, W of P U, comma U. Okay. So, and W dash X to VC is equal to W of XV minus W of PV, comma V minus W mean. Okay. So now I have found out that 10, 12. So and max is 12. Okay. Now what is the if I have to find out? So if it has the original weight X3, so if then I have to recalculate it. It is nothing but W X3 minus W P3, comma 3 minus W mean. So this is the formula. Okay. Now how I find it? So do you know this one? How much is this one? WP33. This is 12. How I got it? I got it by back doing the maximum. Okay. And what is the W mean? W mean is 10. So this is the maximum, this is the minimum. Fine. Now what is now what I'm saying that if WP33 is equal to 12 and W minimum is equal to 10, then W dash XBC is nothing but W X3 minus 12 minus 10 is equal to W X3 minus 2. if W x3 is equal to 4, then new weights are 4 minus 2 is equal to 2. If W x3 is 0, then new weights are 0 minus 2 is equal to minus 2. If W x3 is minus 4, then it become minus 4 minus 2 is equal to minus 6. Okay, so this appeared that minus 2, this minus 2 and minus 6 are, this simply means the original edge with edge weight wx3, which might already be small or even negative in this negative score approach, is not enough to beat the penalty. So what was our penalty? Penalty was 12 minus 10, which was 2. But we got minus 2 and minus 6. If wx3 is 0, wx3 minus 4. Fine. Now, so that's why, uh, eh, because we have seen some negative results here. So, so that's why mm, this level 3 and 2 on the edge XBC typically indicates the reweighted edges is specifically referencing the case where we use node 3 or 2 inside the cycle as the pivot. So this means if we use the minimum version, so the WXP is small, we can easily get a negative score WXBC. That's why you see, so here that means that this minus 6 here, this minus 6 here says, so if you use that you if you use edge level, so you see edges are labeled here. So if WXP is small, you can easily get a negative WXP. That's why you see edges as labeled minus 6 3 if you go with the node 3, and if you go with the node 2, then you will get minus 2. Okay, so the final one, so I am writing you the final one. If it helps, so it basically the original age score minus the parents age in cycle minus baseline among the cycle. Okay, so this is the thing, this is how we calculate it. Now we had to solve this one. So here you have to find the right arc, left arc, reduce and shift. So here you will be using the arc visual parsing. So then you have to find out this one. How to do it? So we had the formula. So the next question is also like same. Like I am showing giving you the showing you the next question also, like correct sequence of action that generates the parse tree of the sentence I love AI course using. So this is the second question. So this is like somewhat similar. So like this is the uh, somewhat similar. So that's why I'm showing to you that correct sequence of action. So here in this I have to specify what are the right arc, left arc, reduce and shift, and here I have to find out what is the what using this arc is a parsing algorithm correct sequence of action that generates the parse tree. So these are the two questions. Okay. So how many first question is how many right are, how many left are, how many reduce, how many shift, and the second question says that a correct sequence that generates this. So first we have to see that what does it means basically the how it work. So if we see like he wrote first word, second word, her, third word, uh later is the fifth word and the whole stuff. Okay. So in this is the subject. Then I have the object. Who it wrote? He wrote to her. So this is the I object. Then what it wrote? What he wrote? He wrote the letter. This is the D object. And then we have a punctuation here. Fine. And this letter has a determinant. Fine. This is fine to you. Okay. So this is the projective level dependency tree for a for a English sentence. Okay. So the dependency parsing problem is usually defined as the task of mapping a sentence where I have some word W1 to Wn to a dependency tree T. Okay. Now ARC is a transition system for dependency parsing. We use we use some list of constructor. So let us see that. So basically transition based. So we are seeing the transition based dependencies here. So in transition based dependency parsing, we use the parsing as heuristic search through a non-deterministic transition system for deriving dependency trees, guided by a statistical model for scoring transitions from one configuration to next. So here I will show you that how R-figure transition system for dependency parsing. The parser the parser configuration consists of a stack sigma, a buffer beta, and a set of arcs. Okay, so what we have? So we have sigma, which is the stack, then beta, which is the buffer, and we also have a set of arcs. Fine. So this is denoted by sigma BA. Now the initial configuration of parsing a sentence. So we denote a sentence by x is equal to, in sentence we know that sentence has some word W1 to Wn. Fine. Now in this sentence has an empty stack. First we have an empty stack, a buffer containing the words W1 to Wn and an empty arc set. So first everything is empty. Then a terminal, so we have to we have to set a terminal configuration also. So the terminal configuration is any configuration with an empty buffer. So so first everything we have in our buffer. Okay. Whatever arcs have then been accumulated in the arc set, A defines the output dependency tree. There are four possible transitions from a configuration where top is the word on the top of the stack, if any, and then next is the first word of the buffer. Okay, let's see how it works. So what I want to say that is this shift, this moves next to the stack. Okay, the reduce of the stack allowed if top has head. Then we have right arc. So what is the right arc? Right arc basically add dependency arc from top to next and moves next to step. Then I have left arc. Add dependency from next to top and off the step. Okay, so this is the case. Now come to our question that how this happens. So here my sentence is given. I love AI codes. Okay. So the love is the main part. Fine. Then I is the subject of the love. Okay. That means I is the subject of the love. Then course is the direct object of the love. That means love, love, course. And AI modifies course. That means course to AI. So here, so what I will have. So here what I will have. So first I have stack. My stack is empty now. What is in my buffer? In my buffer I have I love AI code. And what are the args? It is also empty. Okay. Now first, the first step is shift I. So if I shift I, then in my stack I have I. Okay. In buffer I have love AI course. Fine. So what I have done now? So I did uh, shift left right uh, reduce. Okay. 1000. So I have shifted I into the stack. That's why I have counted uh, here count so far that shifted I. Okay. Now the second step is left arc love to I. That is fine. So this is the left arc. Fine. Okay. So here, what is that? What was in my top of the stack? I had I. So in arc measure, a left arc means the buffer item is head to the stack's top. Okay. So so which is the buffer item? Buffer item is love. Love head to the stack's top. Here we want love to be head of I, which is exactly what I have drawn it here. This one. Fine. Now what I have what the action I created. I created a left arc. I pop I from so created. So I created a left edge. Here I have created it. This one. So that's why I have written it. Created a left arc. Then I have pop I from stack. Right. So what I have done. So my shift is 1, my left arc is 1, my right arc is 0, my reduce is 0. Fine. Then the in third action, what I will have to do? In third action, what I will do? I will do shift love. Okay. That means in my stack, I will have love only. This is my stack because I have already popped I. So this I already popped from the stack. Then I have in my buffer I have AI and course. Mhm. So what are the arcs? I have love to I. Okay. So here what I did, I have shift to left arc 1, right arc 0, and reduce 0. Fine. Got it? Is it clear? Now what I have to do, I have to shift AI. That means I have to shift the AI. So move AI from the buffer to stack. So in my stack, I have love and then I have what I have to do. I have to left force. Okay. That means that in my stack, in my stack, I have love. In my buffer, I have force. So in my arc, I have love to I and force to AI. So that means I have to change it here also. Force to AI. Fine. This is the left arc. See, fine. So here until this point, my shift is 3, left arc is 2, right arc is 0, reduce is 3. Fine. So here my right arc is log to 4. Okay. Here I don't have in stack, I have love and ports, and buffer I have nothing, and arc is love to I, ports to AI, and love to ports. Okay. That means I have to end here. Love to ports. Got it? That means shift 3, left arc 2, right arc 1, reduce 0. Here reduce ports. Right? So here I have to so I have to here I have to reduce the ports. Okay, that means now the buffer is empty. So first I had a love and C. So I have reduced ports. The buffer is empty now. Uh, Course already has a head love, so we can safely pop it. Okay, got it? So we already has a so this course already has a head love. Okay. So that's why we are popping this course. So this course has a head. So that's why we are popping this from the stack. So that's why the count becomes shift 3, left arc 2, right arc 1, reduce 1. Okay, fine. 1, 2, 1, 3. Fine. And so the answer will be 1, 2, 1, 2, 1, 3. Okay. And the correct syntax of this one, this is shift. So first what we have done, we have done shift, then shift, then left arc, then shift, left arc, then shift, then what we have done, then again we have done shift, then left, then right. Shift, left, then okay. So this should be the thing. Fine. So the option is giving like this, but in my assumption, this should be the right answer. Okay, fine. So that's all from my side. So thank you everyone for joining. Okay, so we'll meet in the next class. Yes. So this here now I mentioned it. So you see, shift. Then sorry, first one was shift. Then I had shift. Then left. So that is SL. Then I have shift SLS. Then I have shift SLSS. Then I have left. Then I have right arc. Right. Oh, then reduce. Sorry, in the next page it was. So this should be the answer. Okay. So thank you everyone for joining. We will meet in the next week. So thanks for joining.